לזכור לבוא לסוף סטופ סטרימינג, זה סוף הכל. אחרי שלא סטופ סטרימינג, אני מחזיר לי פסקל.
אז אני משאירה את זה.
כן, בסוף הוא יאסוף את זה.
אולי אני משאירה את זה.
כן, כאילו אחרי כל זה
הכל בסדר. פשוט גם ככה בעצם השכר מדריך
אני לא מבין את זה גם. בסוף אני אקפל את כל מה שצריך אחר כך. שאני לא אהיה פה עד אני יכול לעשות.
זה לא מעניין אותי. זה לא מעניין אותי. לא מעניין אותי.
מה לי חדש זה כפתור? פעם זה היה... חדש? זה שזה חשמלי.
שזה אמור להיות ירוק.
מה קשה לעשות כזה שמושכים? זה לא מה זה עושה? לעשות כזה שמושכים, לא צריך תחכום.
אני פשוט לא אגיע לזה. לפעמים ברגע שזה לפעמים אנשים לא שמים לב ואז זה הולך טיפה בשיפוע. ברגע שזה הולך לי טיפה בשיפוע
יהיה גם מומחה היום?
מה זה כל שבוע פורמיניפרה? כל אחד אתה נותן את הפורמיניפרה.
רק בגללם או לבחור. שלם בייס.
לא,
ביהלומים. אני עושה ניסוי בפורמניפרה, איזושהי קבוצה של 50 מאוד,
שהופך את ובסוף הוא מאמץ אותם, מייבש אותם.
כן, ומה אתה רוצה?
הוא הופך אותם לאמן בו.
למזלי, בדקתי עם הדברים האלה, כל מה שלא יאומן, לא נחשב היה לצורכי ניסויים. אז אני צריך לקבל מישהו מהלסינקי לעשות ניסויים, רק ביוטי. עשית תהליכים ועקומים, דגים חופשיים.
Okay. Hello everybody today. First of all, I'm very glad to see all of you here. You know, the courage people that came today. I'm very glad to see that there are a few second year students here also, which is nice to see. Today we have Nadine Boeing, and Dana did all her degrees in the University of Beersheba, the University of the Negev, and now she's doing a postdoc also there, a short postdoc before she's going to a postdoc in Bristol, and she's going to continue in a way to talk about the last seminar that we had on Foraminifera. Okay, go ahead.
Okay, so thank you so much for having me. And today I would like to share with you the research that I've done during my PhD and postdoc in Ben-Gurion University in the lab of Sigal Abramovich under the joint supervision with Barak Harut from IOLR and Ahuva Almog-Levin from Geological Survey. Mainly, my research deals with the response of benthic foraminifera to rising temperature and expected rise in basically global warming, but also it deals with the use of these organisms as proxies for anthropogenic activity. And in today's talk, I will try to show you both of these aspects of my work. So, I know that last week you already heard about Foraminifera, but still a very brief reminder to why Foraminifera are so awesome. It is actually worth listening to them, about them for 2 weeks in a row. So these are single-celled eukaryotes, globally found in all marine environments. They are extremely abundant and diverse. They are considered to be major carbonate producers and ecosystem engineers. And as they calcify their shell, they actually document the water chemistry and environmental properties within the chemistry of the shell. So as their shell accumulates on the sea floor, they basically create an archive of changes in environmental conditions, and this is why they were also valuable to the field of paleoceanography and in reconstruction of past oceans. So starting to talk about climate change as part of global warming phenomena, the Mediterranean is also warming. And as you can see in this figure, the eastern part of the Mediterranean is warming much more rapidly than the rest of the basin. And this is why it's a great location to study the effect of warming, because the ecosystems who live in the easternmost part are already exposed to kind of extreme conditions, and they start to show the response that ecosystem will have in other places, which is why in many papers the Eastern Mediterranean was referred to as a miniature ocean that mimics what will happen with climate change. So my research started next to the electrical power plant in Hadera. This is because the power plant pumps water year-round to cool the turbines and then discharges it back into the sea, creating a thermal anomaly of about 1.5 kilometers along the coast. This basically provides a very unique opportunity to see what will happen to organism and ecosystem with warming under natural conditions. So what we did is that we monitored this area for a duration of 1 year in monthly intervals. And here you can see an illustration of the heat plume in spring and in autumn. This is taken from the report of the electrical company. And on top of that, you can see two of our sampling stations. Here in red, station H2 at the core of the plume, where temperatures are the highest. And here at the edge of the plume, station H4, marked in green, where temperatures are only slightly elevated from the current temperatures of the Eastern Mediterranean. And we also had an additional station, a control station, in the nature reserve of Nachsholim, which is 18 kilometers north to the power plant, so it is obviously not affected by the discharge of warm water. So basically what we wanted to do is to see over a year, so also getting the seasonal effect, what will happen to the foraminifera communities with the rising temperature in the near future, represented in H4 at the edge of the plume, and then in the further future at station H2 at the core of the heat plume. So at the beginning of the study, we installed temperature loggers in the 3 stations. We stuck them on the rocks. And these loggers record the temperature every 15 minutes. So they created an almost continuous measurement, so we can see all of the extreme events of cold and warm temperatures. And here you can see the documentation in the 3 stations. In blue, you can see the control station in Nachsholim. So this is basically the temperature regime for 15 months, just in a coastal environment in the Israeli coast, and temperature ranges somewhere between 10 degrees in the extreme in winter, and then it reaches about 30 or 31 degrees in summer. In green, you can see the station H4, the station at the edge of the plume. So we're talking about an elevation of, in average, about 1.5 degrees. So it represents somewhere in the relatively near future. And then in red, you can see the station at the core of the plume, station H2. You can see temperatures are much higher than there. It reaches about, in the peak of the summer, in the extreme of the summer, it reaches about 36 degrees. So it's quite far away in the predictions of warming in our area. So basically, just to describe what we did, we went every month to each of the stations. We took the reading from the loggers. We also monitored other environmental parameters like salinity, pH. We took water samples to see the water chemistry and the nutrient concentrations. This is basically just to see that all the parameters are the same except for temperature. I should note that next to the electrical power plant, there is a desalination factory. So the brines are being discharged with the warming water. So there is also an elevation of salinity there. However, it is not very large. It doesn't go over 1 per mil. And we concluded that the salinity, at least when considered with the very extreme temperature, doesn't affect the foraminifera. So for this talk, I'm not going to talk about salinity at all. And along to monitoring all the environmental parameters, we also collected algae samples with the foraminifera who lives within them. And we sorted them in the lab according to species, so we could see the changes along the temperature gradient. And here you can see basically the summary of all of this research, and what we saw is that the ecological monitoring of these 3 stations basically divide the common species of the hard-bottom Israeli Mediterranean into 3 groups according to their distribution in the thermal gradient. So basically according to their thermal tolerance. So the first group marked here in red are 4 species who live in all of the station, even at the core of the plume throughout the year. So basically these species are tolerant enough to experience these very high temperatures, as I said, going up to 36 degrees. Then we have the second group of species marked in green. These are species who live just at the edge of the plume, but not at the core of it. So basically they are resilient enough to experience a small elevation of about 1.5 degrees, but basically not much more than that. And then we have a third group of species marked here in blue, and these are species who are very common in the control station, but doesn't occupy the plume at all. What this means is that these species basically live so close to their thermal threshold that in the relatively near future, they will have to migrate to the northwest of the Mediterranean, creating a trailing edge of these species. So the implication of these results is basically that warming in the Eastern Mediterranean will have consequences in 2 phases. The first one in the near future with the rise of about 1.5 degrees, and then a second one. And it is also very obvious that each of these groups, the resilient, the sensitive, and semi-sensitive species, will be affected differently. So from now on, we'll talk about each group separately. Sorry, one second. Yeah, so let's start to talk about the most resilient species. In some aspect, these are the most interesting species because these are the species that will continue to live in our area throughout the warming process. And what you can see here is the numerical abundances in the red bars of each of the species in station H2 at the core of the plume throughout the 15 months of monitoring. And the black line is basically connecting the monthly average temperature as they were documented by the temperature loggers. And we thought it was very interesting that we saw that these three species, basically everyone except for Paravotalia, shows a decrease in the abundances between April and May. So when temperatures reaches about 30 degrees. So basically this is their threshold. And only Paravotalia continues to show high abundances through much longer of the year until between June and July or July and August, when only then abundances decrease. And this is when temperature is much higher, about 33 or 34 degrees. So this is an evidence that Paravotalia is actually a much more tolerant species. So we were very interested in the fact that they live in the plume throughout the year, but we wanted to ask ourselves, okay, so these species are resistant enough to live there, but are they just surviving or are they doing well? And basically what we wanted to know is, do they just survive or do they actually calcify there, which is a great indication that they are doing well because they're keeping up all of their physiological abilities. So we focused on two species. This is Paravotalia, that is obviously the most resilient species, but also Lachanella that has very high abundances, much more than the other three species. So it's also an indication that it's a species with great potential to deal with warming. And we wanted to know what was the actual classification temperatures that they, or what are the temperatures that they actually calcify in the heat plume, even in summer. So I already told you that we had the logger, so we have a continuous or almost continuous measurement of temperature. We wanted to compare that to the actual classification temperature, so if we see the differences, we can say something about the threshold for this activity. So we wanted to use magnesium-calcium calorimetry. Magnesium-calcium ratios increase with temperature in the shell of Foraminifera, and the main idea was to take the shells that we collected over a year, analyze using laser ablation single chambers, look at the last chamber, and see the extreme temperatures that they can calcify. In order to accurately infer the temperature of classification from magnesium-calcium, we did culturing in order to calibrate this proxy for each of the species. So we grew both of the species, Paravotalia and Lachanella, in three temperatures, 20, 25, and 30 degrees. And we use two independent markers, so we will know which calcite we want to measure when the culturing is over. The first marker was calcium staining. We do this as a preliminary step to the experiment. We put all of the Foraminifera under ideal conditions, and we let them grow in calcium. Calcium is a fluorescent stain that connects to the calcite as it precipitates, and so it gives a visual indication of whether your foram grew or not. So basically, when we start the experiment, we're going to have something like this. We're going to have one chamber that is marked with calcium. Then we move them to water with a lithium chloride spike. So then during the experiment, they are exposed to the conditions that we want to examine. There will be an increase in lithium in the shell. So when we measure it later, we have an indication that this is definitely calcite that was produced in our experiment. So here you can see some of the results, and on the upper panel you can see Paravotalia here and Lachanella here. In the colors, the orange specimens cultured under 20 degrees, in green 25, and in purple 30 degrees. And you can see that magnesium calcium is, as expected, increasing with temperature. And you can also see that the lithium concentration of the cultured specimens is much higher than that of the field specimens that are marked here in blue. So this is how good the indication of the lithium spike is basically working. And because we were very confident in which measurements we could use to calibrate, we did linear regression of these results to get the relationship between magnesium calcium in the shell and classification temperature. And then we inferred that on the specimens that we collected over the year of monitoring from Hadera and from the control station. So let's start looking at these results. Here you see the results for Paravotalia. I'll just give a small explanation about these graphs. Up here you can see the results from station H, so this is the core of the heat plume in Hadera, basically a future scenario of warming. And down here you can see the station of Nachshalim, so just the condition as they are, the temperature as they are today. The black lines are the minimum and maximum temperature as recorded by the loggers, and the little pink squares are the actual classification temperatures as inferred from magnesium calcium. So let's start by looking at the highest temperature. The highest temperature obviously in summer in the Hadera station, and you can see that classification temperature and measured temperature are similar. This is an indication that the species is not limited in classification, at least up to 36 degrees. And what was also interesting is that we saw that none of the specimens calcified under 22 degrees. This is the dashed pink line that you see in both graphs. We couldn't find any specimens from the field that calcified under this temperature. This means that this is the minimum threshold for classification. Now, if you look here in the Nachshalim graph, again, this is today's temperature in the Eastern Mediterranean, you can see that in much of the year, even the maximum temperature of the water is lower than the minimum threshold for classification. This means that this species cannot actually calcify through kind of a large portion of the year. And what this means is that as temperature continues to increase, this species will be able to calcify throughout more of the year, so it will actually benefit from future warming. So now looking at the same kind of graph, but this time for Lachanella, the second species that is very abundant in Hadera, and looking again at the warm temperature, we can see that the classification temperature and measured temperature are very similar. So again, no upper threshold, at least up to these temperatures. And again, a minimum threshold, but this time much lower, 15 degrees. So basically, it can calcify through pretty much all of the year, but even with relatively mild warming, it will be more productive in carbonite production throughout more of the year. So basically, this is an indication that these two species are kind of the winners of climate change in our area. And as temperature will continue to increase, they will become more prominent as carbonate producers. Okay, so now moving on to talk about the less fortunate species that will have to deal, it will be harder for them to deal with rising temperatures. But before I talk about the sensitive and the semi-sensitive species, I would like to mention another very important phenomenon that dramatically affects the ecosystems of the Eastern Mediterranean, and this is the Sepsian invasion. This describes the phenomena that organisms migrate through the Suez Canal from the Red Sea to the Mediterranean, and what is interesting is that this is a selective process. Not all species go through. Some species are not able to migrate and establish populations, but those who do often do it in such a successful way that they take over the ecological issues and sometimes pushes away some of the local species. Another thing that is known about the Sepsian invasion is that it is facilitated by warming temperature, by the ongoing warming. So basically it means that it's an ongoing process and that as temperature continues to rise in our area, more and more species will be able to invade. The reason that I bring this up now is that many of the species in the Israeli coast, the Foraminifera species, are the Sepsian invaders, but specifically both the sensitive and semi-sensitive species have all been proven using molecular methods. They have been proven to be the Sepsian invaders. And for this reason, I thought it would be interesting to look at their thermal tolerance in context of the invasion. So the first example will be this species. It's called Untitled Chapter. It is an extremely successful invader. It is now established population through the entire Eastern Mediterranean, all the way up to Italy. In the Israeli Mediterranean coast that we monitor regularly, we see that in many locations, this guy is presenting more than 90% of the Foraminifera in many locations, so very successful. But what is interesting is that in this genus there is another shallow water species, Amphistogina lesoni. So you can see that these guys are very similar. You don't need to be an evolutionary expert to see that these guys are related. And if you go to the Gulf of Aqaba or anywhere in the Red Sea, you will see in the very shallow environment many specimens of these two species. Basically, if you pick up a rock, it will look like this. All the little circles are marking Amphistogina specimens of both species basically in the same abundances. However, as I said before, if you go to the Mediterranean, only Amphictyonal bifera is present. So this is an observation that indicates that when this is a very successful invader, this one is not able to invade. And we ask ourselves, what causes this selectivity in invasion in such closely related species? And we hypothesize that this has something to do with temperature, because we know the invasion is facilitated by warming. And looking at the different temperatures in the two marine environments, we can see, starting to look at the maximum temperature, that in summer, the Eastern Mediterranean is very similar to the Gulf of Aqaba. And more than that, as temperatures will continue to increase, the Eastern Mediterranean will become more similar to the Red Sea, which is a very warm area. Now looking at the cold temperature, at the minimum temperature, we see much more prominent differences. We see that the Eastern Mediterranean is a much colder environment than the Gulf of Aqaba and most of the Red Sea. So in order to examine this hypothesis that this is what causes one species to be a successful invader and the other to not show up at all in the Eastern Mediterranean, we use the alkalinity anomaly method. This is a very commonly used method to accurately assess or calculate the calcium carbonate production of calcifying organisms. This is because each mole of calcium carbonate that precipitates lowers alkalinity by 2 equivalent moles. And we've actually adopted this method from Jonathan Lehrer's lab, but we've established it very well, and as you can see, we use it now as a very central tool in our research. And the first thing that we wanted to ask, as I said, is whether the temperatures are a limiting factor for Amphictyonal lesoni to invade. So we collected specimens from the Gulf of Aqaba of both Amphictyonal bifera and lesoni. We of course separated them to 2 different groups. We cultured them under 6 temperatures in the range of 15 and 35 degrees, basically to cover the entire range that these forams see in the Mediterranean, and also adding on two future scenarios, one in the relatively near future at 32 degrees, and another one at 35 degrees, also correlating to what we saw in Hadera, so maybe we can try to make sense of all of this together. And we cultured them for 3 weeks. Each week we replace the water in their bottles and measure the alkalinity of the water, comparing it to a control station, a blind sample with no foraminifera in it. So we can know what is the calcification rate. We can calculate what is the calcification rate of each species in each of the temperatures. So for both species, 15 and 35 degrees is not good for them. They are both sensitive to it. As you can see in this graph, they basically stop calcifying completely. And the first difference that I want you to notice between the species is actually in 20 degrees. So Amphictyonal bifera, this is the invasive species, increases the calcification rate between 15 and 20 degrees. It stays around optimum calcification rates in 20 and 25, and then shows some decrease. While Amphictyonal lesoni, this is a species that does not invade, shows a mild increase between 15 and 20, and then an additional increase between 20 and 25. So looking at these differences, we can assume that Amphictyonal bifera is more resilient to 20 degrees than Amphictyonal lesoni. It should be noted that during the 3 weeks of the experiment, there was some increase in calcification rate at 20 degrees from Amphictyonal lesoni. This indicates that this species can acclimate in relatively short time to 20 degrees, and looking at this, thinking of the future warming, this indicates that with a kind of mild increase in temperature, the species may be able to also invade the Mediterranean. So now looking at the warmer part of the temperature, to try to think about future scenarios, let's start again with Amphictyonal bifera. We see a decrease between 30 degrees and 32 degrees for the invasive species, but for the non-invasive species, we see that the classification rate only decreases between 32 degrees and 35 degrees. So this basically means that the Amphictyonal lesoni is not only more sensitive to colder temperature or to 20 temperatures, but it is also more resilient to higher temperatures, until somewhere between 32 and 35 degrees. So if we try to conceptualize what will happen with these species with the future rise in temperatures, Amphictyonal bifera will no longer be able to live in the Eastern Mediterranean. It will have to migrate to the northwest. Around the same time, Amphictyonal lesoni could already invade, and because it can deal with the higher temperature of 32 degrees, it will basically possibly take over the niche of Amphictyonal bifera. So the other question that we wanted to ask was whether after many generations in the Eastern Mediterranean, basically since the invasion, multiple generations have evolved. They've been exposed to very different or a much larger temperature range, and we wanted to see or try to see if this affected their thermal tolerance through adaptation or acclimation. So we did another experiment. We went to the Mediterranean, we collected Untitled and we did the exact same experiments. So 6 temperature between 15 and 35 degrees for over 3 weeks. And we compared the results of the Mediterranean population and the Red Sea population. So looking at the differences between 15 and 20 degrees, as I said before, the Red Sea shows an increase between 15 and 20 degrees to optimum value, and the same thing happens in the Mediterranean population. However, looking at the warmer temperature, we can see that while the Red Sea population decreases between 30 and 32 degrees, the Mediterranean population already decreases the gasification rate between 25 and 30 degrees. So basically, the Mediterranean population show higher sensitivities to elevated temperatures. There is still more to be done to say this is really adaptation. We do think that this could be related to a mechanism of selective invasion. This was shown for corals, that during invasion, only specific strains succeeds to actually do the invasion, and this is because of trade-off between conditions. So what we think is possible, but we still need to do a lot more work to actually say that, is that this is some kind of trade-off between their ability to deal with the cold temperature in the Eastern Mediterranean on the expense of being better at warm temperatures. So there is another very interesting thing about benthic foraminifera that I have not yet mentioned, and this is that many of them host algae as symbionts. So basically this is a holobiont where the foraminifera is the host and the algae is the symbiont. And we were interested to know if the thermal tolerance of the holobiont is synchronized between the host and the symbiont, or whether one of them could be a limiting factor for their future in a warmer world. And I just want to say at this point, and I will come back to that, the different foraminifera species have completely different kinds of symbionts. So Amphitidina has diatoms, but other foraminifera have red algae or dinoflagellates, and this also adds a lot of interest into checking the thermal tolerance of both parties of the holobiont. So starting kind of where we left off, we wanted to examine the thermal tolerance of the host and the foraminifera. So we did another experiment, and we again checked classification rates, but also photosynthesis. So basically, we wanted to see the thermal tolerance or the well-being of the foraminifera, the host, and of the algae by looking at the performance of photosynthesis. In classification, we saw the same thing that we saw before. So no classification at 15 and 35, an increase between 15 and 25, and then a decrease between 30 and 32, and an additional decrease to 35 degrees. Looking at photosynthesis, we saw something completely different. We saw that photosynthesis is not reduced at all at 15 degrees, but there is a reduction between 25 and 30 degrees, and 32 degrees, and additional decrease between 32 and 35. So we see that there is an asynchronous response of the host and the algae, and this will obviously control some of the biogeographical distribution as temperatures continue to change. So now let's move on to talk about the most sensitive species. These are the species who are very common in the entire Israeli Mediterranean coast, but do not go in the plume at all, not even at the edge of it. These guys, as I said before, are so sensitive to even a mild increase in temperature that they cannot tolerate this small increase. And this was very weird to us, because both of these species in this genus, we expect them to be thermally tolerant for multiple reasons, but these are the main ones. Soraites orbiculus was extremely common in the Paleocene Eocene thermal maximum, so you would think that by evolutionary processes and adaptation, it will have tolerance to high temperatures. And Pneroplis actually today inhabits in very large abundances the Arabian Sea and the Arabian Gulf, where temperatures are much higher than the Eastern Mediterranean. So we thought, this is kind of weird that they don't go in the plume, not even at the edge of it, and we wanted to examine that. So, as part of a bachelor project of a very bright student that is now joined our lab, I supervised our project, and we did 2 experiments, one on Soraites and one on Pneroplis, to try and see what's going on with their thermal tolerance of the host and again of the symbiont. So just to mention that Soraites orbiculus has dinoflagellates, so more similar to coral and very similar from Fistigina that has diatoms. And Phaneropolis has a rhodophyte, some sort of red algae, so completely different systems of holobionts. Kind of. Let's start by looking at the Sorites. Looking at classification rate, we see that in the first week, between 25 in the range of 25 to 35 degrees, there was no response or no changes in classification rate. In the second and third week, there was a small decrease in classification rate, but also nothing major. So if you remember on Fistigina, at 35 degrees, doesn't calcify at all. It's not able to do this basic physiological activity for a foraminifera. But this one, it shows some decrease, but it's definitely not as dramatic. So basically, you can say that Sorites is quite resilient to thermal tolerance. However, if we look at the performance of the algae, if we look at photosynthesis, we see that from the first week, photosynthesis is already reduced. And also we see that during the second week, it is already reduced to 32 degrees. So basically this kind of works with the fact that they live in the, basically in all natural environments in the Eastern Mediterranean, but are not able to tolerate the small increase at the edge of the plume because their symbionts are just too sensitive. So now moving on to Phaneropolis, this was a shorter experiment, only 1 week. But there is still something that can be learned from it, and we can see that classification is pretty similar between 25 and 35 degrees. However, photosynthesis, so the well-being of the algae, is lower at 25 degrees and at 35 degrees than at 30 and 32. This could be an indication that basically the symbiont algae has a very limited range that they are happy with. And I think that this is a very interesting species to study in respect to its large abundances in the Arabian Gulf, which is basically the best field laboratory for warming today because it is so warm there. Okay, so this is an overview of the stuff that I did related to the response of Foraminifera to rising temperature. And now I want to move on to talk about the second part of my research. Basically, the main idea is to use Foraminifera as very sensitive, very effective indicators to coastal industry. And basically what we want to do is to use the shell chemistry as a proxy for pollution. Obviously, this is not really new. This has been done in paleoceanography to reconstruct past environmental conditions. There was also work published using Foraminifera to recognize in their shell the chemicals that are, so there were published papers that used Foraminifera shell as proxies for industrial pollution in present, not in the past. However, there was something very interesting that we saw that because of that we think it will be a very useful and very important method. So let me just start and let me take you back to the beginning of the talk that I explained to you that we monitor the Hadera power plant in Nachsholim, and this is great also for this value because this is a nature reserve and this is an industrial facility. However, they are both considered as clean environments. So the area next to the electrical power plant is being monitored regularly and the results are published because the electrical company has to do it, but also we monitor this area for 15 months. And if you remember, what I said is that we collected water samples and we analyzed it for major and trace elements, and we saw no indication of pollution. Basically, using both water analysis and ecological monitoring, we could say that this is a clean environment in a similar way to Nachsholim, other than the temperature disturbance. And since we used the shell chemistry to do the whole magnesium-calcium project to see the threshold for classification, we also got indication about other elements. And what we saw is that several elements, all metals, copper, zinc, and lead, all show elevated concentration in the shell collected from Hadera. Now, please understand, these are all shells that we collected from the same places, Hadera and Nachsholim. Nothing was different. The water didn't show any elevated concentration. However, the chemistry of the shell definitely picked up this footprint of the industry. So this is why we know now that this could be a very sensitive indicator, much more than the traditional methods. Another thing that I would like for you to note is that the values of concentration within the shell of Lachlanella, this species here, were higher than the concentration of this Foraminifera. And again, these were all specimens that were picked from the same place. Basically, take a bunch of algae and then under the microscope, you take the forms away. So these group together saw the same concentration, but their incorporation is different. And Paraotania incorporate less metals. I'm not going to go into detail because this is not related to my own research, but the possible explanation to the different concentrations in the shell of Pararotalia and Lachanella is related to the fact that they have completely different shell types. That is a result of completely different classification mechanism. Very briefly, Pararotalia is a hyaline shell. This basically means that it calcifies shell on a template in an extracellular process, while the miliolid species, Lachanella, or the miliolid shell, is produced in a very different way, where the calcite needles are produced intercellularly and then pushed out. So this could explain where the concentration between species who see the same water, the same concentrations, show such different concentration. And while Lachanella might have an advantage by showing very high concentration, so it would be a good proxy, Pararotalia has a different advantage. And that is that this species builds its shell chamber after chamber. So basically the chamber here marked in 1 is the last one calcified, and it presents a specific event of classification. So a specific time frame where it documented the water chemistry. The chamber marked in 2 was precipitated before that, so another specific time frame that is documented, and so on. And basically what this means is that if you collect enough specimens from a specific location, you can kind of trace back the metal concentration in the majority of time. So basically, Foraminifera are like little data lockers that just live in the sea and documents the water chemistry for us. And here in this graph, let me just explain how this works. This is the copper to calcium ratio in Achsholim in July. This is copper calcium ratios in Chadera in May. The little dots are the concentration in the first, second, third, and fourth chamber. And the color indicates that the chambers are of the same specimen. So basically, all of the red ones are the same, all of the green ones are the same specimens, and so on. And what you can see here are two interesting things. First of all, if you look at the baseline in Achsholim, the nature reserve, you can see that almost all specimens show values of below 5 micromoles to moles. Basically, this is the baseline. So most of the time, the concentrations that you get, if you look at the Pararotalia shell, is this. However, if you look in Chadera, you can see that the baseline is already much higher, even double, and it reaches 10. So basically, this is the constant footprint of the electrical power plant that we couldn't pick up by water sampling or by ecological monitoring, but the Foraminifera definitely recognize it. What was more interesting or would be more useful is that we see that specific chambers have higher concentrations. If we start by looking at the Chadera example, you can see that some of the third chambers and one of the fourth chamber show a much elevated concentration of copper, which means that at time of classification of these chambers, there were elevated concentration in the water. Basically, this is an indication of some short-term event that was captured by these specimens. Now, looking at the Achsholim, we see the same kind of thing. We see that many of the fourth chamber and one of the third show elevated concentration of copper. Now, in Chadera, it kind of makes sense because we know that the power plant, when it takes water to cool the turbines, it adds copper to get rid of the algae growth. So we can understand that, okay, it's diluted in the water, but I guess the forams are quick enough to pick it up. We just understand where this pollutant is coming from. In Achsholim, we don't really know where it's coming from, but the reason that I show this is that this is exactly the example of why we think that this is a very important method that needs to be implemented, because it can recognize short-term events of pollution that are overlooked by traditional methods. This is just a conceptual way to show the method. Before I demonstrate it, I just want to say that the traditional method that I keep talking about consists of mainly water sampling. So you take the water and you measure the trace major elements. And this is a direct indication to the concentration in water. However, you cannot sample all the water all the time, everywhere. It's limited by resolution. And so if you sample it once a month or once a week or even once a day, you still might miss some events of extra pollutants being inserted in the water. A second very common method is sediment sampling. So when you sample a sediment, you get a time average signal, and if it's a short-term event, it might be diluted in the larger way. Also, in many environments, you cannot sample sediment, like the entire northern coast of the Mediterranean, which is a rocky environment. You can't actually sample sediment there, so it's not applicable. Another very common method is analyzing organic tissues of organisms, which is very good because it gives an indication about the bioavailability of the metals. However, it doesn't produce any kind of continuous measurement, so again, you might miss specific events. And this is why we think that this is a good method, because basically if you go to a polluted area, you're not going to have any problem knowing that it's polluted. You can sample water, organic tissue, sediment, and so on. And if you sample foraminifera or any kind of shell, you're going to get homogeneous, high values throughout the shell. If you go to a clean environment, and if it's indeed clean all the time, you're going to see kind of homogeneous concentration of metals within the shell. However, if you go to a clean environment that experiences some short-term events of elevated pollutants, you can then see that through most of the time there will be low concentration, but then specific chambers will show you elevated concentration. This is basically the results that I just showed you in the previous graph, where, I'll just show it again, where some chambers of specific specimens show elevated concentrations. So even though this was done before, and many people show, both in field observations and laboratory experiments, that the use of foraminifera shell chemistry can be used to monitor pollution. The reason that we think that this is so valuable is because it can actually monitor these specific events in a quite simple methodology. So, as I said, this has been used before. We're not the only one who think this could be useful, and probably at least some of you know this graph by Harry Elderfield that describes the confidence that we have in the proxy as time goes on and we use it. Pretty sure we're still in the optimistic phase, but I'm sure we'll have to go through the entire thing. And so, in order to try and raise the amount of confidence that we have in this proxy, we wanted to ask two major questions. The first is whether temperature is affecting the incorporation within the shell, because if it does, the seasonal effect of temperature will just make the whole proxy completely irrelevant. So that is the first question. And the second question is if we can use different species to use this method. Basically, we already saw that Lachlanella and Parvotalia have completely different values, so obviously they cannot be compared. And some species are local, so if I use Untitled Chapter and someone doesn't have that species, he cannot use this method. He has to calibrate by itself. It's going to be uncomfortable or not. It's not going to be easy to use. So we wanted to see if we can find a group of species that we can use globally in different parts of the world to make it an applicable method. And then, of course, the main goal is to characterize the relationship between concentration in seawater in shell to make it an actual proxy. So we know that when you picked up this forum, it recorded in the last few months two short-term events of elevated pollutants. So we did a couple of experiments. I just want to say this is all very preliminary. This is very much work in progress. But just to get you interested, and I would like to also get your feedback on that. So first, we examined the temperature thing because this is obviously a deal breaker, and we collected Amphistogena lobifera. We chose Amphistogena because it's such a common species that is abundant in many environments in the tropical and subtropical latitudes, and we cultured them using the same two independent markers that I described before. So we know that the calcite that we measure is actually the calcite that grew under assumed conditions. We cultured them under 4 concentrations of zinc and of lead, and in 25 and in 30 degrees. And when we do laser ablation analysis to see the concentrations, we see that it's similar in both temperatures. So we were very happy about that, and we wanted to take the next step. And the next step was whether we can use species of the same genus to work out the system. So we took, again, Amphistogena lawsoni and Amphistogena lobifera, and we cultured them under 3 concentration, again, of zinc and lead. And when we analyze the shell, we see that both species also show the same concentration. So we were very happy about that too. And then we did an additional, so this is a compilation of everything basically that we did. It's everything that you saw, but it has also one more concentration. Because we think that this would be an optimal method for what is considered clean environments, we wanted to check the entire range of clean environment and did what is called the CCC. This is basically the criteria imposed by the EPA for what is the chronic exposure, what is the concentration that the chronic exposure will damage the ecosystem. So the CCC is marked in the dotted line here and here for each of the marker, and we were very close to what we think and a little bit past it with the lead. Let's just start by looking at zinc. You can see again that the temperature doesn't affect and the species doesn't affect. There's quite a nice linear relationship between the concentration in the shell and the concentration in seawater. So there's still work to be done, but we feel very optimistic about it. Now looking at the lab, we're a little bit surprised that adding the higher concentration kind of completely lost the linearity of it. We think that we should do a lot more work basically in this area here to either characterize the relationship between the concentration or define what is the range that we can use this proxy in, or maybe come to the conclusion that for lead, maybe because it's much more toxic than zinc, it's not possible to use this method. But still, to get confidence in this proxy, we need to do this for lead and for many other elements, and also for other species. Yeah, so this was an overview of everything that I did in my PhD, plus the almost the last year. And I just want to finish with just 1 minute of what is happening next. So next week, I'm moving to the University of Bristol to start a postdoc under a fellowship from the Royal Society. And I'm really happy about that because this actually gives me an opportunity to kind of connect with the geologist in me. And as you understood by now, I've cultured many specimens of Foraminifera under different temperature, measuring the stress level. And the idea of what we want to do is that we want to take these cultured specimens, apply on them different techniques, examine their crystallography, geochemistry, and morphology, and trying to find some evidence of the stress in the shell, basically a thermal stress signature in the shell that we can then apply to the geological record. Then we want to go to fossil from the Paleocene-Eocene thermal maximum. We feel that this is the best analog because there are at least 2 species of large benthic foraminifera that we have cultured specimens of that were very common also back then. And we want to try and look of sections at the PETM, try to find this signature along the section correlated to temperature using magnesium calcium, and try to see if there was, over the multiple generations that experience the warming in the PETM, if we could see changes in their tolerance, in the temperature in which they showed this signature. And hopefully I will be able to tell you more about it if you invite me again during this postdoc. Thank you.
Thank you very much, Nana. Questions?
I think it's an excellent presentation. It's the second time I'm hearing your talk, and you're getting better.
Thank you.
And I have a suggestion to make. It might be a little bit you do not like it. Is to stop using the laser ablation.
Stop using it.
Yeah, and replace it with a micro drill that you can still drill a specific chamber and then use a regular ICP-MS. I think you'll get better results because you'll be able to better calibrate the signal than under the laser ablation. I think that the laser ablation introduces a lot of uncertainty into the analysis.
I would really like to continue this conversation, and maybe also with Jonathan, even though he might not like it, just to really understand it.
We've done some comparisons where we take larger foraminifera and laser ablate the chambers, and then break the chambers because we know because of the calcium mark, and then we compare the two. And for certain elements, it is identical, but for others, it's not identical. And it is very difficult to understand why. It could be that in the laser ablation system, it's very difficult to contaminate. While you take the broken pieces of the foraminifera and you dissolve them in acid and you introduce it into the mass spectrometer, then during the process you may contaminate. Okay, so who knows? For trace elements.
I think
that's it.
I think it's definitely worth exploring, especially if you say that some elements are more sensitive or less sensitive. We're actually also in the process of trying to see if we can use this method just using whole shells or multiple shells. It's kind of a lowering of the method to be more commonly used. We're actually trying to do that right now in geological survey. But yeah, I think it's definitely worth exploring.
מותר מעבר. אני רציתי לשאול על הפרמטר של הזיהום, שהוא בעצם, את יכולה לראות אירועים קצרים של זיהום, אבל הזיהום עדיין מתחת לרמה שהיא טוקסית בעצם. והשאלה, בעצם בסופו של דבר, למה זה שימושי? כי סך הכל אם זה היה זיהום חריף לזמן קצר, הוא היה נמחה לחריף. הזיהום האחרון הוא לא היה בעייתי, אבל פורמיניפרה היה מת, ולכן את לא יכולה לראות. אז בעצם יכולה לראות רק אירועים קצרים מתחת לרמה שהורגת אותם.
כן, אז זה נכון שזה, אני חושבת, כנראה בטח בדוגמאות האלה לא מגיע למה שנקרא פולושן באופן פורמלי. אני גם חושבת שיש לזה ערך, כי קודם כל בתור כלי רגולטורי. אוקיי, אז אנחנו יודעים שסביבה היא מזוהמת או לא מזוהמת, אין לנו מושג מה קורה באמצע. בדוגמאות האלה הריכוזים אולי לא כל כך גבוהים, אבל יש המון סביבות של תעשייה, שלא בטוח שאנחנו יודעים בדיוק מה מתרחש בהם. ואנחנו גם לא נדע אם לא נבדוק. עכשיו לדעתי, זה סתם ניחוש, אבל זה כאילו מלראות מה קורה בים, וכולנו רואים זרימות של נערים שלא צריכים לזרום, אנחנו מבינים מה נשפך שם. אז זה יכול להיות דרך לנטר בעצם מה קורה שם, פשוט ברזולוציה יותר טובה. האמת היא שעד שלא נעשה את זה, לא ממש נדע אם צריך את זה או לא, אבל אני חושדת שבמקומות רבים מאוד בעולם אנחנו נראה שיש ערך למצוא אירועים כאלה, שבהם הם אולי אירועים כביכול קצרי טווח, אבל הריכוזים בהם מאוד גבוהים. ואז אתה רוצה לדעת...
אם זה ירוק, זאת אומרת, זה תראי שמתים, פשוט תראי מה הסף, זאת אומרת, את מחפשת את הטווח, כשזה מאוד מאוד גבוה, זה ירוק אותם.
כן, אז זה לא, כן, אבל הרעיון הוא כאילו למנוע זיהום לפני שהוא קורה. עכשיו, יש פה קצת, זה קצת לא קשור לגיאוכימיה או זה קצת כזה תהליך פסיכולוגי, שאתה אומר, אנשים, תעשיות, הם עושים מה שבא להם, כאילו אם הם לא ירגישו שיש מישהו שמסתכל עליהם, אז אתה כל פעם גונב עוד קצת, גונב עוד קצת, והרעיון הוא כאילו ליצור שיטת ניטור שלא מאפשר את הספייס הזה. יכול להיות שאני סתם בן אדם חשדן וסקפטי, אבל אני חושבת שזה כן עובד ככה.
איך בדיוק האם את יכולה לתארך, כאילו, האם את אומרת, אוקיי, אני רואה את זה בחדר השני, אבל מתי הפורום הזה גידל את החדר השני, ואם אחר באותו זמן כבר מגדל את החדר הרביעי שלו?
כן.
איך נכנסתם עד הזמן?
זה אכן מעט, אני לא רוצה להגיד בעייתי, אבל זה אכן איזשהו משהו שצריך להכיר בשיטה הזאת. אי אפשר ממש לתארך, כאילו לא יכולה להגיד, ב-13 בספטמבר קרה הדבר הזה והזה. כלומר שוב, ודרוש פה עוד מחקר כדי להגיע לנקודה הזאת, אבל אנחנו מכירים פחות או יותר את הזמנים שפורמיניפרים גודלים בהם, ולכן אם אתה אוסף, נגיד, אני יודעת על פרווטליה, שהרבייה שלה בים תיכון קורית באפריל, ולכן אם אספתי אותה בסוף אפריל, אז אני רואה ממש את החברים הצעירים, אם אני אוספת במאי, אני רואה צדדים קצת יותר גדולים, ובעצם אני חושבת שאפשר לעשות איזשהו סינכרון לדבר הזה, כדי לקבל, שוב, זה לא יהיה כאילו on the mark בדיוק מתי זה קרה, אבל איזשהו estimation של פחות או יותר.
משהו כמו השוואה בין טבעות של עצים.
כן, אז זהו, אז האמת שזה גם משהו שאולי שווה להגיד, השיטה הזאת משתמשים בה הרבה עם צדפות, וזה בגלל שיש להם את הבנדים של הגדילה, וזה נותן באמת time resolution. ועושים דברים ממש ממש יפים בעולם הזה, כאילו בשימוש בשיטה הזאת, אבל אין להם קליברציות של הריכוזים בין השלד למים, ולכן זה הופך להיות קצת פחות כאילו ניילינג. אבל כן, כאילו לאורגניזמים שונים יש בנפיץ שונים, וצריך להתחשב בזה.
I have also a question. When you talk about short pollution events, how fast it takes, or what's the time frame of building a new chamber? Because you need to build it just when the pollution happens, no?
Yeah, so I think this is a very good question. I think it also changes dramatically between different species. There are a few species that we know, that we see it in the laboratory, how much time it takes. It can take several hours for them to produce the...
Several hours?
It can take several hours for them to... For specific species, but I think some species might take longer. But this is a part of the calibration that... Sorry.
It may depend on the age. When they are small, they build one chamber per day. But when they are bigger, they build one chamber per week. So...
Yeah, but the main classification event doesn't take away. The main classification event is quite short. It just takes them longer to get more and more chambers.
כמה זמן הם חיים?
זה גם משתנה מאוד, ממקום למקום וממין למין. החברים האלה בים תיכון יש להם מחזור חיים של פחות או יותר שנה, אבל נגיד המפיסטיגינות בים תיכון הם חיים שנה, ובאילת יש להם, הם מתרבים פעמיים בשנה. אז כלומר, זה גם כנראה קשור למשרות טמפרטורות המאוד שונות.
באמת ש-22 מעלות לא מצליחים לבנות שלג. אז לגבי זה כמה שאלות. אחד, האם בימים קרים שמאוד מזוהמים אנחנו מפספסים לגמרי את הזיהום? זו שאלה ראשונה. שאלה שנייה זה האם אנחנו יכולים ללכת ל-Environments ולבדוק את הפורמניפרים שם בקריטון או בסדר, ולהגיד, אוקיי, תקופות שלא היה לי בהם השקעה, אולי הטמפרטורה הייתה תיקח ל-22 מעלות, ואני יכול בעצם לפתח איזשהו פרוקסי חדש להשקעה או לא של תנאי קרבונטים.
אז כל חושב שזו שאלה מצוינת, היא בעיקר מצוינת כי היא ממש ממש מעסיקה אותנו כאילו בקבוצה. זה נכון, מינים שונים, יש להם טווחי טמפרטורות, וראינו את זה ממש טוב בפער אורטליה ולחונלה, טווחי טמפרטורות ספציפיים שהם משקיעים שלג. וזה אומר שבחלקים מסוימים של השנה אנחנו לא הולכים לקבל מהם תיעוד של שום דבר, כי הם פשוט לא משקיעים שלג. אז חלק מהתהליך שהפרוקסי הזה צריך להפוך כדי להיות משהו שהוא ממש אפליקבל, זה לקחת איזשהו סט של מינים, ולראות, אוקיי, זה מין שעובד בחורף, זה מין שעובד בקיץ, בתקווה יהיה גם איזשהו אוברלאפ ביניהם, בתקווה אם הכל יהיו מינים שהאינקורפוריישן בהם יהיה אותו דבר, או שנצטרך לקהל אותם ביחד, אבל ראינו שצריך ממש, כלומר, זה, מה שאני ראיתי זה פוטנציאל, זה לא שיטה. והאמת טוב, אני בדיוק עוזבת, אבל קיבלנו עכשיו גרנט בקבוצה של סיגל, באמת לעבוד על הפרוקסי הזה ולבנות אותו. וזה מורכב מהמון המון דברים, שזה קשור ללהבין איך אפשר פחות או יותר לתזמן את האירועים של הזיהום, וזה קשור ללהרכיב איזשהו סט מינים שמכסה נגיד את כל השנה, וזה קשור גם ללהבין אולי עוד גורמים שאנחנו עדיין לא ממש מבינים, כמו נגיד משהו שאנחנו כבר יודעים מניסויים שעשינו ולא הראיתי, זה שיש פורמיניפרים שפשוט לא גדלים בריכוזים, אפילו לא מאוד גבוהים של מתכות, אז obviously הם לא קנדידטים לדבר הזה. עכשיו, בקונטקסט של פלאו, אני עדיין בינתיים לא מומחית לפלאו, אבל אני חושבת שזה עובד פחות או יותר הרבה דברים, צריך לקחת מינים שונים ולהשתמש בהם כמשהו רציף. כי אתה יודע שלא כל המינים יתעדו את הכל, אז אתה חייב לייצר איזשהו רצף של ההבנה שלך של הפרוקסי במינים ספציפיים. עונה?
Later. Okay, thank you very much, Dana. תודה רבה לך. אני לא מבין בזה כלום, אבל זה היה לי מעניין. את רוצה שאני אמחק את הזה שלך?
כן. סתם יש על זה כל מיני קומנטס מוזרים שלי עם עצמי.
זה